Please. Yes. It is different from everything else. And that's, well, maybe I should just say that's the subject of a whole other colloquium. But remember I told you that the W only couples to the left-hand parts of the electron and the quarks. So you see this in many aspects of the weak interaction. For example, electrons in beta decay, you can measure directly their polarization. It's preferentially left-handed. And the more relativistic the electron is, the closer it gets to 100% electron polarization. Now, neutrinos are extremely light. It turns out neutrinos have mass, but the masses are very small, below 1 eV, where all the masses I was talking about here are MeV or GeV. So when a neutrino is emitted by the weak interactions, it's always extremely relativistic. And so it has essentially 100% left-handed polarization. And then you can use that effect to do various particle physics measurements. You can also confirm that by using neutrinos as a beam to scatter off of protons. There are specific aspects of that process which basically show the helicity of the neutrinos and show that they're purely material. Other questions? Please.
Coming from condensed matter, the analogy with superconductivity means that the vacuum is a condensate, right?
Yes.
How can we see it, besides the excitation of the Higgs, that there is some stiffness and there's some energy density or something that comes with condensate like in condensed matter? There's no signature of that, right? There's
well, so there are the quantum excitations.
Right.
So as I said, there are, so in a superconductor, typically the quantum excitations are the phonons, and they get sucked into the massive photon and become part of the plasma excitations. So here, that is the W boson. And so in some sense, you see that through the W polarization and top decay that I showed you. In superconductors, the oscillation in the size of the condensate is typically not a large effect, although there are some superconductors where that can be seen. And the quantum of that is the Higgs boson, the analog of the Higgs boson. So there are some superconductors in which you can excite that particular mode of oscillation. And here we can't excite it macroscopically, but we can excite it quantum by quantum and study the particle.
Yes, but you're talking about the excitations. I'm talking about the ground state.
No, but the ground state is all around us.
Right, so how do we see it? I mean,
well,
except for these theories, I mean, is there a direct measurement of the ground state problem?
Well,
like
no, I mean, to do that, you would have to like take something the size of this room and inject into it 100 GeV cubed per a cube of size 1/100 sorry, please excuse me. You would have to inject in it roughly 1 TeV per cubic Fermi of energy. Okay, and I'm sorry, I don't know how to do that.
And it doesn't have any influence on gravitation or
Oh, well, that's another interesting problem. In principle, it should gravitate. But if it did gravitate, then the cosmological constant, the dark energy, would be larger than what we observe by a factor of 10 to the 60. However, in the strong interactions, there is another symmetry breaking that I didn't talk about called chiral symmetry breaking. And that we understand perfectly how it works. It's basically a condensate, a quark pair condensate that condenses into the vacuum. And that gives rise to properties of the pion. It can be tested in many different ways, and this theory is very well established. And that, if it gravitates, would give you dark energy larger than observed by a factor of 10 to the 40. So this is another mystery, which I don't understand, but somehow it validates the fact that I'm not worried so much about this gravitational effect. Other people worry about it. For me, I think, well, there are many problems. You have to figure out which is the next one you're going to solve, and I don't think that's going to be. Other questions?
Okay, let's thank Michael again.